Hello and welcome to Psych319, Chapter 2, Part 2. So we recently were talking about the star-faced, or the star-nosed mole. I keep getting that wrong. And what I wanted to, the reason I bring up that species is to highlight the differences interspecies variation. So if you were to draw a map of the star-nosed mole's somatosensory cortex, you would see that those little appendages on the front of their nose occupy roughly 52% of their somatosensory cortex, which just shows you how important that appendage is in their lives. They need it all the time. By contrast, their whiskers and hands receive a very small percent of somatosensory cortex. Now this is a cross-section, a coronal section of the human somatosensory cortex. So the ear would be out here. This is in Japanese. Sorry for the language difference. But what you can see here is for us, our hands occupy a huge part of primary somatosensory cortex, and our nose occupies a very, very small amount, because the nose is very is not as important to us as our ability to navigate through the world with our fingers. So what's also interesting and is the notion of phantom limbs, which I'm sure you've heard about. When people have an amputation, they lose a hand or a foot, they have the odd sensation that the limb is still there. They feel that they have sensation, tactile sensation, a sense of touch in their missing hand, which we know can't be because there are no fingers there. And this has been a puzzle for a very, very, very long time. And while the whole story is a little bit complex, the basic idea is that you remove the hand, but the brain representation is still there. And with that brain representation just sitting there, it starts to take on the job of encoding sensations for other parts of the body. So you get a lot of cross wiring between brain areas, and input areas from other parts of the body start to feed into that hand area that is now dormant, and then you get the odd sensation of touch in a limb that doesn't exist. Or another example would you could have a patient with a missing arm. You would stroke their face, and they would feel it in their face, but they would also feel it in their missing phantom hand because of the interconnectivity of these two areas. The reason this is a serious issue is because we have phantom limb pain. Sometimes amputees can have a sensation of pain or cramping in this limb, and it's a very difficult problem because you can't amputate further. The limb is gone. They have a phantom sensation of pain. And the original thought was that it came from the nerve endings, but you could amputate further up the arm and further all the way up to the shoulder, and it didn't seem to help. And that's because, of course, the sensation of pain is in the brain. This happens for other limbs. You have phantom arms, feet, eyes, even phantom uterus after hysterectomy. So women could experience the reports of phantom menstrual cramps, even though they didn't have a uterus. And what appears to be going on is the brain has learned to be in pain. So if you have a case where the arm, let's say you had a cancer in the arm, and the brain was in pain for several years, and then suddenly you amputated, well, you're very likely to have phantom pain there because the brain has learned that the hand was in pain and agony before it was amputated. On the other hand, if you got in a car accident and immediately just lost that limb, the brain didn't have time to learn that the body was suffering from chronic pain, and therefore you tend not to get phantom pain in that particular instance. So it's an issue of learning. So how can you correct this? One clever way, designed by Dr. Ramachandran at UCSD, was to develop a mirror box. So here Dr. Ramachandran is demoing the box. He actually has a left hand, but he's tucked it up here to make it look like he's been amputated. And he put a mirror in between the right field and the left field. So if he's looking through the mirror, he can see his working right hand and a reflection of the right hand off the mirror. So it kind of makes it look as though he's got a working left hand. And then he'll do a number of exercises using both hands. And what happens is the brain starts to receive feedback that it has a healthy working left hand. And when you do this in patients, they start to learn that the arm is not in pain. They report having diminished pain over time. I'm going to show you a little movie of this in another patient. Um, and this patient here was doing the same type of therapy but with a video game. So he does not have a left hand. He's wearing virtual reality goggles. And he's playing a game where he's asked to do a bunch of tasks using both hands. You can see the glove on his right hand is tracking the motor movement of his right hand, but he's only getting visual feedback from the left hand. And he reports that this is a really useful therapy for him and greatly diminishes his phantom pain. So I'm going to talk about a bunch of brain systems, not necessarily individual structures, but several systems that are responsible for major things in the brain. I'm going to start with the limbic system. And the limbic system is generally for motivation and emotion, and it involves several structures, most importantly the hippocampus, which we associate with memory, the amygdala for emotion, and the cerebellum, which is involved in a different type of learning. Cerebellum is, of course, back here, but it's also associated with motor movement. What happens when the hippocampus is damaged? So when the hippocampus is damaged, um, as in this patient, so this is a famous patient, H.M., who only died a couple of years ago. He was a very valuable patient in psychology. He was having, I believe it was epileptic seizures, and so they went in and performed a surgery and they removed both his hippocampi. It turned out to be disastrous because he had no ability to form new memories. He could remember things from childhood and anything in his past, but if you walked into a room, introduce yourself, and walk out of the room, he would forget who you were in 5-10 minutes. I highly recommend seeing a movie called Memento. You can get that on Netflix or wherever, rent it, because it sort of portrays what life would be like if you don't have the ability to form new memories. It's very, very difficult to navigate through the world. Of course, and he's still intelligent. He can still add, subtract, play games, and things like that. He just has no ability to form new memories. Another case study is a woman who had damage to her amygdala. And so here is this patient performing a bunch of facial expressions on the left panel, and they're from happy, sad, disgust, anger, and so on and so forth. And she could produce the facial expressions, but she couldn't recognize her own facial expressions. She couldn't tell which ones were happy or sad or surprised, etc., which demonstrates the role of the amygdala in the recognition of emotions. And this is a patient with damage to his cerebellum. You might notice that he walks much like a baby. He stumbles occasionally. He has to recover his balance. You know how babies are learning how to walk. They're learning how to associate the timing and sequence of motor movements in their limbs to the effects of moving those limbs. So they might try and take a step forward and then stumble a little bit, and they have to learn that coordination. And that's what the cerebellum is involved. It's involved in the timing of things. So when we say it's important with learning, we say it's important in making close associations in timing. So if you think of Pavlov's famous experiment with the dogs where you ring a bell and the dogs eventually, and then you feed them food, eventually the dogs will start to salivate only when they hear the bell. The reason is the cerebellum is involved in making a close association between the bell and the food. The cerebellum is, again, responsible for timing. Let's see. Now, moving on to another system. That was the limbic system. I'm going to talk briefly about the basal ganglia and the thalamus. Now, the thalamus is a very easy structure. It's really the switching station of the brain. You could think of it as Times Square or Grand Central Terminal for the brain. It's where all the information comes in and is routed elsewhere. It does have its own functions, but that's typically what we think of when we think of the thalamus. And then you have a bunch of other structures, the caudate nucleus, the putamen, and the globus pallidus. And all of these are part of the basal ganglia, and they are responsible for the control of movement. And these are what's affected when you have Parkinson's disease. I'm going to go into this in a little more detail. So think about when you're learning how to drive a car. When you're first learning how to drive a car, you do that thing that only new car drivers can do. You get the gas and clutch and brake all going at the same time, and the car starts to shake violently. Um, but eventually, over time, you can learn to say, oh, I just want to go forward, and then your brain takes care of all these automated tasks for you. It does the clutch, the gas, the steering wheel. It does them all in one smooth, coordinated movement. And as a result, you could just do things like turn left, go forward, without having to think of anything more complicated than turn left or go forward. But when you're learning how to drive that car, you have to think of each step individually. And that's kind of what the basal ganglia does. It takes these deliberate procedures like clutch, gas, steering wheel, and so on forth, and coordinates them. So with practice, the basal ganglia is allowed to take over intentional tasks and make them automated. So in Parkinson's disease, there's a lack of a particular neurotransmitter called dopamine, and that results in rigidity and tremors and difficulty in controlling movement. So if you ever watch somebody with Parkinson's try and sit in a chair, um, they look like they're learning how to sit in a chair for the first time. They have to put one arm down and put another one down, and they might be shaking. And this is not because they lack the physical strength to do that. Sure, they're typically old, but it's not that they lack the physical strength. It's that the brain has lost this ability to automatically do simple tasks, and so they have to think about things as individual and using intentional thought. At the opposite end of the spectrum, you could have a disease like schizophrenia, and that's marked by hallucinations, delusions of grandeur, delusions of persecution, and that's also caused by damage to the basal ganglia. So a very odd relationship between Parkinson's and schizophrenia. If you have too much dopamine in the basal ganglia, it causes schizophrenia, and then you get hallucinations and psychotic behavior. But not enough dopamine produces Parkinson's-like symptoms, and then you have rigidity and tremors. So these diseases appear to be at the opposite ends of the dopamine spectrum. And if you want to see a nice summary of that, there's a movie called Awakenings with Robin Williams, and that tells you a lot about the schizophrenia story, but actually that is a very romanticized caricature of the true story, which I believe you can find on a show called Frontline, where in the real story there are patients who had taken a bad batch of synthetic heroin and overdosed on the drug, and it profoundly affected their ability to control their motor behavior, and they ended up becoming locked in their own bodies, kind of a locked-in syndrome. And I'm not sure what the specific link is that, but if you do a search on schizophrenia or a compound called MPTP, and for the show Frontline, you'll see a fantastic show on this and learn a lot about the basal ganglia in that system. So I'm going to stop here before we get onto the hypothalamus and continue in the next session.